Hi everyone. This is Sourav Roy. He will be the first speaker for this session, and he will be talking about approximation of mixed volumes of convex bodies.
Thank you. So let's start. So let us first see what are the convex bodies we meant by and what are the mixed volumes. So convex bodies in Rn, we are taking the convex sets which are compacts and whose interior is non-empty, which is a non-empty interior. Okay. And we will look for two properties here. So there are two convex sets here. But there is something about strongly convex set. So the strongly convex set refers that if you take any 2 points from the convex set, if the line joining them lies in the interior of the convex set, then we'll say it's strongly convex. So you can see this is strongly convex, but it is not, because this for the points in edge, this line lies in the edge, not in the interior. So let's move ahead. So we have two convex sets, A and B, a box and a rhombus. So take any point x from A and take any point y from B, and we are looking for the point x plus y. So all such collections we'll take a collection of it and we'll call A plus B, and this A plus B is called as Minkowski sum for two convex sets. So Steiner formula gives us the volume for the Minkowski sum for two convex body K and B, where this lambda is a non-negative parameter, which will help to scale the B as you want. So it turns out that this expression is become a polynomial in lambda itself, and these coefficients AI are given by this factor, this expression, and here this is called the mixed volume corresponding to the index I. So the ith mixed volume, here we have n minus I copies of K and I copies of B. Okay, I'll give you an idea what visualization of what is this things in the simpler setup. So this n here, the dimension in which you are taking the sets. So I will give you examples for n equals to 2 and 3. So when n equals to 2 in 2D, so we'll have, there are three terms, A0, A1, A2. And when n equals to 3, there will be three terms, A0, A1, A2, A3. Okay. So this is an example in 2D. So we have a disk, we have a polytope that like a triangle. So here are the A0, A1, and A2 term. So correspondingly, we have given, so this is the Minkowski sum for these two objects. And there is a, by the color, you can see the segregate how the mixed volumes look like corresponding to the each terms. Similarly, if we have in 3D, we have four terms, A0, A1, A2, and A3. So we have a sphere here, we have a cube here. So here I haven't considered all of the parts, just few parts to make you understand that where are the mixed volumes corresponding to the each term lies. Now you can see one thing from this picture. So there is a lambda factor here. So as lambda increases, this ball is increasing. So what will happen in this picture is that the A0 will remain fixed, but this pink region and this blue region is getting sky region is getting increasing as lambda increases. Okay. So in today's talk, I will work with a polytope K and a ball that is strongly convex, and I will look to my motive will be to find out the volumes, mixed volumes of A0, A1, AIs in n dimension. Okay. So what is the difficulty here is that so what one might can do a random walk in this body and try to look for how many points fall in the different regions and to get a sample out of it and try to find the volume out of that method. But the point is, the difficulty is that it might happen in the n dimension case if you have a polytope given by ax less equals to b. It might happen for the ith skeleton the mixed volume that is supported in the ith skeleton can be very tiny, very small, but in exponential number of pieces. So in that case, your random walk will not take points from that skeleton, and but the point is the total area for the corresponding mixed volume, ith mixed volume, can be non-negligible. So that was our difficulty here. So we will take a polytope given by this equation. The K contains origin and the K is not too flat, not too large. That is given by this condition that it will contain a ball of radius smaller and bounded by capital R. The aspect ratio R by small r, its logarithm is bounded by poly n. And the second the second object, the ball in n dimension, represented at the origin, and the radius is R tilde. So our goal is to approximate the mixed volume terms occurs in volume of K plus lambda b. So in n dimension, we have A0 to n plus 1 mixed volumes. Okay. So again, from here you can see that for the A0 term and An term, the volume, the mixed volumes are nothing but the volume of the polytope K and the ball respectively. So our job is to just to find the mixed volumes that is lie between 1 to n minus 1. So before having proceed, we have three oracles access. The oracle B1, what it does, if you query lambda to B1, it will give you approximation of the volume of K plus lambda b. If you query lambda to B2, it will output a sample I from 0 to n with the probability ai lambda to the power I by the full polynomial. But note that we don't know this quantity. But we have access to pick sample I with this probability. The oracle B3, if you feed lambda to B3, you will get an empirical distribution d hat lambda with a probability vector r hat in n plus 1 dimension. Okay. Now let us see what this happens. So the lambda is non-negative, so you can choose lambda from 0 to infinity. Okay. So this graph here, so along the x-axis I have the integers 0 to n. Okay. And along the y-axis, this is the probability of picking point from the ith mixed volume. Okay. So when when you are taking a lambda 1 below this quantity, you are getting points from the 0th mixed volume, that is from the point from the body, convex body polytope itself. Okay. So, and this 1 by n to the power 3 is some threshold for every lambda 1, lambda 2, lambda 3, lambda 4. So, and if you take lambda large enough, like if you take lambda more than n log n by t log n, that is lambda 4, then you will observe to take points from the corners, that is from the nth mixed volume. And in between that, for lambda 2, lambda 3, you will pick points from the mixed points. You will pick points from the intermediate mixed volumes. Okay. So what you can observe here that as lambda increases, the peak the threshold above the threshold move from left to right. Okay. So if we want to find a mixed volume for the kth mixed volume, we need to pinpoint a lambda such that the curve lies above the threshold at k, that is something like lambda 2. We need to find such lambda 2. That is our motive. So what is the main theorem? If you fix any point in between 0 to n, if you take a t greater than 10, then there exists lambda in this interval such that tk lambda is at least 1 by n to the power t large. So with 1 by n to the power t probability, we can pick point from the kth mixed volume. So we need to find such lambda. So for that, we will require noisy binary search to do it. So this is the starting interval. So the interval is L0 log of t log n by n, and the upper hand of the interval is log of n by t log n. Okay, we are doing a binary search is in log lambda space, not the lambda space. Okay, so this interval may can contain 0 also. So the what is the iteration step? The lth iteration step is that you are looking for the midpoint LL by RL by 2, and we are calling by log lambda. Okay, now from there you can get back to the lambda space, what lambda you are picking in the log lambda space. There is a one-to-one bijection. Since this is a lambda to log lambda is a monotone curve, so you can do that. So from log lambda you can get the lambda L, this one. This lambda L you are querying to the B3 oracle, and you are getting empirical distribution corresponding to the that is we are calling a d hat lambda L. Okay, so one of these three situations can arise for the d hat empirical distribution look like. So it might that the threshold will already above k at lambda L. If this happens, then we'll output the lambda L, and that will be our required lambda L for the corresponding mixed volume k and the fixed t. If it happens that k lies left to the empirical distribution, that means that the threshold is towards the right side, the peak is towards the right side from k, then we will choose this interval for our next iteration. If the empirical distribution look like this, then we will choose the other half of the interval for the next step, and we'll go on. Now by this binary search, we need to ensure that this should end in Polyton steps. Okay. So for that, let us visualize how it happens with the pictorially. Okay. So the one thing that very well known facts that this AI is a log concave. Okay, we'll use this fact here. So here AI is a log concave, so we are putting on the x-axis the integers 0 to n, and on the y-axis we are putting log of AI. Okay, and we will get this concave curve where p0 pk is of the point k comma log ak. Okay, this sequence from this is the sequence log lambda n is from getting from the noisy binary search that is approaching towards some true log lambda. Okay, that we don't know. Pictorially, what is happening at pk? We have a tangent whose slope is log lambda, and there is this red curve and the green curve of log lambda n minus 1, log lambda n slopes respectively. So as we are approaching from the in the noisy binary search, we are getting as L increases, we are getting this slopes, this tangents are getting closer and closer to this blue line. Okay, but now we want to show that to ensure that this binary search ends in Polyton steps, we need to focus on this fact, that is given k in between 0 to 1 to n minus 1 and fixed t greater than 10, we have that IKT is at least 1 by e to the power Polyton large. What is IKT? IKT is the interval in the log lambda space such that for any log lambda in this interval, the corresponding probability of picking point from the kth mixed volume is at least 1 by n to the power t large. So if I can show that this interval is at least this large, then we are done. So for that we have this lemma 2. So the lemma 1 is saying is that if we have a tangent whose slope is log lambda prime at k, and if we look for the vertical distance from this tangent to each pi, then there is a relation between the vertical distance with the probability to pick the points on the jth mixed volume. If this vertical distance is not too large, that is t minus 2 log n, then the corresponding this lambda prime, the picking point, the probability of picking point from the jth mixed volume is 1 by n to the power t. So note that the roles of k and j can be reversed. So what we require by so you can see here that these tangents are getting closer and closer to the blue tangent, right? So if we can get a tangent, if the green tangent is vertical distance from the green tangent to the pk, if that is bounded by t minus 2 log n, then the probability corresponding to this lambda n, the probability of picking point from the kth mixed volume is 1 by n to the power t large. Okay. And when this will happen, so that is followed by the lemma 2. The lemma 2 says that, so what you have done here, so the k cannot be, it might not happen that k is the peak of the concave curve, right? But what we can do, we can take a linear transformation to make this curve as a peak point. Okay. So that is the linear transformation tree that we did, so that the k is the maximum point for the log concave curve. Now this is the transformed tangent, that is TLK. So at J1, if we take any J1 point such that the tangent at J1 makes an angle theta j with the tangent at TPK, then there is a relation between this angle and the vertical distance. So what is the relation? Is that if this angle is not too large, that is t minus 2 log n by omega n, then the vertical distance is bounded by t minus 2 log n. And for that lambda, you are getting this tangent. Corresponding to that lambda, you can get that the probability of picking point at k is 1 by n to the power t large. Now, this quantity itself, 1 by, so you have a flexibility of choosing j from here to here. For which theta can be at most this large at least. So this is itself 1 by e to the power poly n large. So that gives you the idea to prove this theorem. And since we have this, so our binary search will end in poly n states. So for each fixed k in between 1 to n minus 1, we can get a lambda in time in poly n stage, so that we can pick the point from the kth mixed volume, and correspondingly we can approximate the kth mixed volume. Thank you.
Are there any questions?
Oh, I mean, is it specific for one of the convex body being a ball, or does it work for?
So the point is that in our setup, we need a strongly convexity. So the ball is a strongly convex set. So if you take my idea is that if you change this ball by any strongly convex set, that is still the theorem should hold. But I haven't proved it yet. So in the B, so if you see, I have talked about this oracle B2, right? Okay, so it can pick sample I from 0 to n with this probability. Okay, so in this oracle B2, we require one property of the closed one property that is called from a point. If you are given a closed set that is K, and if you point outside, you need to find a unique closest point to the body. Okay, so if you in a different norm, that is L1 or L infinity, the unique closed point property may not hold in other norms.
Meaning there is no unique close point, or meaning you can't find it?
So there is the unique close point property is not hold. So what I mean that what I meant about that, suppose we are in a L1 norm, okay, and this is and if you point here, and we are looking for the a point that is minimizing over this polytope to check that polytope either is in this region that is separated on the corner, or on the edge, or on the body itself. So if the point is here itself, and if the unique close point property may not hold, then you might find 2 points, that is one is here and one is might be other. So the oracle will not give a right answer to choose either the 0 or the 1 as your output. So we need the unique. So in L2, that case is not there.
But I was thinking that the distance is still Euclidean, just that the body is not a Euclidean ball. It's a, let's say, a diamond, Nelson ball. So there'll still be unique closest point.
Yeah, so if you work with, suppose I am working with here a box, not a ball. Okay, so here you will get a box instead the ball, right? Now if you look for the problem that minimizing point, so the point is that this segregation doesn't hold. So this partition, this is a clear partition you can see with the mixed volumes course and the regions that I have drawn here. So if you change this, there is no guarantee the same partition will hold. It might happen that there is a different partition hold. So with respect to this setting, this partition hold for any polytope K and any ball.
Okay.
Are there any more questions?
Thank you. I missed the first part of your talk. So I want your comments on the following. So can this be applied to optimization, for example?
Optimization,
So there are many instances where you use binary search to optimize things. So the idea is there's a noisy oracle. I don't know the function value exact.
the noise,
Oracle that is, so here you will require function values, right? That's the way we'll use binary search optimization. Your result is saying that you have some interesting thing to say with the binary search is noise.
yes.
Now, can that be translated to, I do not know the function value exact. I hope, is that problem statement clear or what I'm asking? Otherwise, we'll talk later.
So this is the noise which is coming from here when you are calling the B3 and you are getting an implicit distribution.
Right.
Yes. And now can you just
Now I'm just saying, okay, first is, can this machinery be used for optimizing certain things?
okay? I don't know yet. I haven't looked at.
Maybe that's what that's.
We
Because
can,
there's a lot of interest in machine learning where I don't know the function value exact.
okay.
So that's the,
I haven't thought about it.
okay, maybe.
We can talk later. Thank you.
There are no more questions.